So you are welcome. Today, what we were supposed to start discussing on Thursday, last Thursday, we discussed today, which is assumptions around hypothesis tests. So look at these verses. There are some maxims here. One says virtually all hypothesis tests are actually the same thing, dressed in different clothes or different names. Another one says, that's my own maxim, but Striner and Norma says something. Nearly all statistical tests are based on signal to noise ratio, where the signal is the important relationship and the noise is a measure of individual variation. Let me just explain this maxim before we proceed. It will give you a clue to understanding hypothesis tests. There's nothing big about it. When I say virtually all hypothesis tests are the same, whether you call it chi-square, t-test, ANOVA, think of any hypothesis test, it's the same logic. And the logic I want to also know tonight is the logic. You see that it's going to be easy for you to understand, to conceptualize this hypothesis test. And what Striner and Norma say, what they are saying is that it's like a signal to noise. If those people that are working with radar try to get signal, they tune the radar, as they are tuning, especially it's just like when you are tuning radio to a radio station. So when you are tuning, you'll be connecting, you'll be hearing noise. The best tune is when the noise, the signal is far higher than noise. You cannot get noise signal without noise. But most of the time, when you say you are okay, it's because the signal is high and the noise is small. So when you now, let's say you divide signal, you make signal the numerator and noise the denominator. If signal is big, more than noise, so what you get will be big. But if the noise is much, which is the denominator, so at the end of the day, your tune will be less than oneself. So that's the logic. So that is what I'm going to explain what signal means when it comes to hypothesis test and what noise means. But just know that it's signal over noise. The hypothesis test, their division is division. There's division there. The logic behind is division. You divide signal, the value of signal, by the value of noise. Because you expect signal to be far more than noise. If noise and signal is the same, you're dividing it will be 1. 30 over 30 is 1. 100 over 100 is 1. 1 million over 1 million is 1. So if signal and noise is the same value, it will be 1. That's so that there's no difference in the signal and the noise. So the noise will be much. But if noise is more than signal, that shows that the value will be less than when you divide something and denominator is bigger than in numerator. It will give you 0 point something. So the value will not even be up to 1. But if the signal is far more than noise, signal, which is the numerator, far, you're going to see what you have will be far greater than 1. So let's proceed. The general formula for a test statistic from what I've just said now, I've already told you it has to do with division. Test statistic is equal to variability between groups over variability within population. Variability between groups is the signal. Variability within population is the noise. Let me just use something to explain. Imagine you want to know, you did blood sugar for a group of men and a group of women. Their blood sugar, averagely, the blood sugar of male, of the men, 60 milligram per percent, while the female, 65. You can see averagely, you can say that female they have higher blood sugar than male. Just an hypothetical example. And the difference is 5. You can see. So that value, 60 and 65, that's what we call observed value. Because when you do your descriptive statistics, will even be that without hypothesis testing, you'll be able to summarize and say, oh, this means for male 60, the average for female is 65. You can see these are observed value. And the difference of 5 is the observed difference. Now, you now see what you are looking at. For you to say, will you now say that the blood sugar of 5, difference of 5 between male and female is significant? That, oh, actually, there's a difference. That, you can see that for female is higher now. There's a difference in the blood sugar between male and female. So, but you cannot actually say unless you put it to test. And the logic behind the test is that because you know that even if the blood sugar of the female is 65, the male is 60. There are some male that have higher blood sugar than some female. Even though their own average blood sugar is lower than female, there are some male that have higher blood sugar than some female, even higher blood sugar than the average for the female. It's only that we have enough that have lower, so that by the time you have calculated the average is 60. Even among female that say their average is 65, there are some female that have far lower blood sugar than some male, and even far lower than that 60. It's only that there are many that have higher, so that by the time you divide it, you calculate the average is 65. Can you see now? So that particular, forget about male or female now. In the population generally, what is the variability in the blood sugar? If the variability is far as that's 5, so finding difference between male and female 5 is nothing, because if you mix them together, which is the population, without dividing them to male and female, and the value of variability there is 5, or even greater than 5, and you are now seeing the variability between male and female 5, why would you not say it's significant? There's a difference. So there's no difference, because that's it. That 5 you see between male and female is a normal thing. It should be a normal variability, or within the normal variability in the population. You will see the variability, the difference you are looking for is the numerator now, which is the difference you observe between male and female, which is different between groups. But the variability within the population is the natural variability. If apart from maybe you divide people into group, male and female, the natural variability, you know that variation do occur in the sense that we see wide differences among people. My own blood sugar can be deep, another person can be higher, another can be lower. So if you calculate the average difference in blood sugar, it can be as high or close to what you observe between the two. If that's by the time you divide it together, you won't see anything reasonable. Maybe if they are equal, numerator is equal to denominator, you give you 1. It doesn't mean anything. Even sometimes the variability within the group in the population may be far higher than the variability you have observed between the two groups you are comparing. In that situation, when you divide the between group within the group now, you will see that you are going to have something less than 1. Because if the denominator is higher than the numerator, you are going to get something 0 point something. That shows there's no difference. For you to prove that variability between the group is so big that it's offset the one within the group, that's the only thing that will tell you that, yeah, the difference I observed between the two groups is really different. So in that situation, it has to be so big that compare with the denominator, which is smaller. When you now divide it to be greater than 1, not only the greater than 1, it can be far greater than 1, that it reaches a critical, it reaches a value. No, this one cannot, this one is too big. It cannot be due to chance. This one is a really different. So that is what we call critical value. And the way they are already social statistics is that when you are calculating the probability, we call p-value, which is probability of making type 1 error, which is probability that the difference you have found between these two is due to chance, which is the p-value. They are already done in such a way that that critical value, that value that when you cross it, once the value, the statistic is above it, you know that you cannot say it's due to chance. They are already done in such a way that value will be equal to the 0.05, which is the benchmark, a cutoff point you have already set for probability for you to reject no hypothesis. So you know p-value is probability, and the probability is from 0 to 1. So if you now choose 0.05, which is 5%, so anything less than 5%, that's, oh, this probability is so small that we cannot say the difference we observe is due to chance. It's a little different. So they will set it out so that that critical value will correspond with that probability of 0.05. So when you are doing hypothesis test now, you're going to have the statistic, test statistic. We are going to have corresponding probability, which is p-value. So what really happens now, as the test statistic is going higher, the probability of with the different due to chance will become smaller and smaller. When that test statistic reaches a critical value, for it to go further like that, the p-value also, corresponding p-value reaches 0.05. So once you need to, the test statistic is becoming higher, the probability p-value becoming lower. You know, oh, this thing is statistically significant. It's only one test, Wilkinson test, which is the non-parametric counterpart for t-test. That's the only statistic that as the value increases, the p-value also increases. For the statistic to be significant, the statistic has to be smaller. As the value increases, p-value increases. But as the value decreases, the p-value decreases. But any other statistic, as the value increases, the p-value goes in opposite direction. So that the higher the statistic, the more likely it is significant, because the corresponding p-value will be less and less. So that you cannot say, okay, the probability that is due to chance is so small. Let's say it's not due to chance, it's really different. So if you now look at the second equation I wrote, you can write in this way, say, test statistic is observed value minus hypothesized value over standard error of observed value. I will explain. So the observed value, let's just use, I usually use t-test, independent t-test, to explain that. Because the independent t-test is the simplest to explain the assumptions around hypothesis test. And that's why I put the independent t-test formula around, just to explain. We are not doing t-test now. It is when we start our individual hypothesis tests that we do t-test. But now, it's just for you to understand. Now, look at what I said here. I said, t-test statistic, that second equation, is observed value over hypothesized value divided by standard error of the observed value. What is the measure of variability within population? Is the standard error. We are talking about it. It's the measure of, because I said standard error is the population standard deviation. That is standard deviation of sampling distribution, but it's said to be equal to the population standard deviation. So that standard error, you see, is the measure of variability in the population among people generally. For any measurement, for any variable you observe, you measure. The measure of variability within the population is the standard error. Now, if it is standard error, if you are looking at the value, maybe mean or proportion, percentage, it is that standard error of the mean or the standard error of the proportion that is the measure of variability in the population. If you are looking at difference between two mean or difference between two proportion, it is that standard error of the difference that is the measure of variability in the population. Now, let's look at this. Then what is the observed value? What is hypothesized value? The observed value, like what I said, the value you see, you summarize, done your descriptive stuff, is your observed value. For example, now, for the female, that the summary, the mean value blood sugar is 60, is 65. For male, 60. When you remove the difference is 5. The observed difference is 5. The observed value for all of them are observed value. The observed mean for male is 60. For female is 65. The observed difference is 5. Now, if you apply it to this second formula now, observed value, which is observed difference, will be 5. What is hypothesized difference? Hypothesized difference is the difference, or the value, is the value when no hypothesis is true. You know, no hypothesis say there is no difference. That's what no hypothesis is. For this case of male and female now, blood sugar, no hypothesis we say There is no difference in the blood sugar of male and female. To be sincere with you, if there's no difference, that should they have the same value. If that is the case, when you now, the difference will be 0. So the hypothesized difference will be 0. So divided by the standard error of the observed value. Now look at this example. This is a formula for independent t-test. If you say t-test, this is a formula. Now, bar 1 minus bar 2, bar x1 minus bar x2. Bar x1 is the mean for group 1, maybe for female. Bar x2 is the mean for group 2, let's say for male. Then the mu1 minus mu2 mean in the population. What is the value for male, female, and male in the population? You know, the bar x is for sample, but mu is for population. And if not, hypothesis is true, the mu1 and mu2 will be the same. When you now minus it, mu1 minus mu2 will be 0. That is what the denominator is the standard error of the difference. It looks complex. That is the standard. You don't need to call me. That is standard error of the difference. You know, we already said that the numerator is observed difference minus hypothesized difference divided by the standard error of the difference. Can you see now? So everything, the square root of x squared 1 plus n1 plus x squared 2 over n2, that is the standard error. You remember we said standard error is standard deviation over square root of sample size. That is what they are put here. If you say standard deviation s over square root of n, but because standard deviation, if you now square, if you want to find square root, you want to extend the square root beyond that n up, it has to be square root of variance. When you square the standard deviation, the square root of variance is still the same thing because the square root of variance is standard deviation. So just leave that denominator. Just know that that's standard error. But where I'm going to is that if you look at the right side now, t now becomes s bar 1 minus s bar 2 over the standard error. That mu1 minus mu2 is out because if not hypothesis is true, that mu1 minus mu2 will be 0 because that is the difference. That is hypothesized difference. Your hypothesis say there's no difference. So that should have the difference is 0. That's why that is replaced by 0. So that's why what you see as this formula for independent t-test. Independent t-test means 2 groups. You are calculating t-test between when you have 2 groups. You are looking at different in the two groups, in the mean of the 2 groups. That is the formula. So if this one is just the same thing, because this one is for pair t-test, leave that one. Because when you get to pair, you understand it. Even this one, just leave. I think you've gotten the gist now. So when we get to t-test, we talk much about the different type of t-test. Now, let's now you have an idea of what hypothesis test is all about. It's about the difference at the numerator divided by the standard error. That is the variability population, which is measured by the standard error. So the difference you try to observe in your sample, maybe difference between 2 groups at the numerator, the difference within the population, which is measured as standard error, is the denominator. So that's all. So when you get to understand it further, when we get to each of the tests, chi-square, t-test, all those things, let's now look at assumption of parametric tests. Now, before you can understand the assumption of parametric, let me just come to hypothesis test, the different type of hypothesis tests. That's where you get to understand what parametric test is all about. Now, you see this table? The table is just trying to different hypothesis tests. Want to classify them. It has classified them anyway. Now you see the first column is about put purpose there. The purpose of the test. What is embedded in that purpose is 2 things: the study design and the type of variable you are dealing with. While the other 2 columns, it talk about the test statistics. The test statistics are now divided into 2 groups: parametric and non-parametric. The parametric, the logic behind parametric is that, parameter has to do with population. So a test that you will do, that the assumption is based, you base it on assumption that your data set follow a particular distribution, theoretical distribution, and that distribution is normal distribution. No, we are talking about this normal distribution under probability. So we talk about normal distribution before we then came to introduction to inferential statistics. So the parametric test, any test you carry out, you assume that that particular data set follow normal distribution. They are called parametric tests. Under it, you see student test, peer test, analysis of variance, which is ANOVA. You can have Pearson correlation, linear regression. All these are under parametric tests. Why non-parametric? The one you cannot assume that, because it's very obvious that that particular thing doesn't follow normal distribution. There are chi-square, Fisher exact test, all different type of chi-square anyway. I just put chi-square for trend, for ordinary variable. We have many type of chi-square. Magnemal chi-square, Wilkinson ransom test, Mann-Whitney U test, Kendall's test, Wilkinson-Shannon test, Krukawali's one way or another, Feynman two way or another, Spearman rank correlation, Kendall rank correlation, and logistic regression. These are not parametric. Let him now explain further. You will see that for each of them, there are the purpose. Each of them has some purpose, whether parametric or not parametric. You will see for some of these purposes, you have both parametric and non parametric. The logic behind it is that originally that variable you want to test, they surely follow normal distribution. But because if there are outliers, I think I talked about outlier the other time. If there are outliers, even though for the example now, which follow normal distribution naturally, but if there are problems with the data set where we have some extreme value, extreme outlier, either extremely smaller or extremely bigger, when you have it, it has skewed the data set. In that situation, the data set is not normally distributed. There is non-parametric counterpart. That is, you can do for that same purpose, you can use a non-parametric that will do the same thing as this corresponding parametric do. That's why you see under each of the purpose along the row, you see some tests that are parametric, some are not parametric. So the one that are parametric, if you are able to meet the assumption that the data you are following, you are using following normal distribution, you use it. If you cannot meet that, you may decide to use a non-parametric counterpart. We should talk much about what inform what you now do for that. If you see that your data set does not follow normal distribution. Let's start with the first one here. Compare proportion between independent groups. This one is telling you another way of saying comparing proportion between independent groups is looking for association between two categorical variables. So here now, when we were discussing the type of variable, we use the most fundamental approach to classify variable. I said variable, if the value you give to the variable is number, is numerical. If it is not number, it's categorical. And we go further to say the categorical is either nominal or ordinal. The numerical is either discrete or continuous. We also say there's an uncertainty classification where you say you can just say the variable is either discrete or continuous. The continuous. Discrete means there are distinct categories. So even ordinal or nominal, they are a form of discrete. So I explained that classification. But here, and I told you that time that sometimes there are different ways of classifying variables. It depends on the usefulness. Now, I want to tell you that variable can be exposure or outcome. Exposure or outcome. Exposure means the variable that lead to something. Outcome is what is being led to. For example, now, if you want to look at association between level of education and employment, what determines what? It's not your employment status that determines your level of education. It's your level of education that may determine your employment status. Or level of education and occupation, or whatever. So, or your level, your employment status. So when you look at the relationship between level of education and employment status, Which one comes first? The one that comes first that will lead to what is the exposure, while the one that something is led to is the outcome. It's very simple. But another word they use is dependent and independent variable. Independent, the word dependent and independent variable in those days were being used by experimental researchers, the people that were involved in experimental research. Now, why the word exposure and outcome is people that are involved in observational study. For you to know, observational study is type of study where you do not do anything, you just go. Observation means you collect data collection. I've already told you. Either you call it measurement or observation, you collect data. When you just go and collect your data, nothing else, that's observational study. But if you influence what you want to study, that's the experimental. For example, if you want to know somebody in level of education, on level of awareness and in level of knowledge, rather, level of knowledge concerning maybe HIV. So if you just go and administer a questionnaire to know what they know about HIV, that is observational. But if you give them health education, or you do peer education, or any form of education, or either counseling or whatever, you inform them of something. You have influenced their knowledge. When you are not asking for knowledge now, if you give education, it will reflect in their knowledge now. It will help their knowledge. That influence, that is experimental. Experiment doesn't have to be something in laboratory. In research, I say, is when you influence what you are studying. For example, you want to measure blood sugar. If you measure blood pressure, you just measure blood pressure. That is observational. But if you give antihypertensive, you prescribe antihypertensive, and you now measure their blood, the antihypertensive have influenced their blood pressure. That is an experimental design. A type of research like is an experimental design. So you can say, once you influence what phenomenon you are studying, it's experimental design. So because your outcome now will now depend on the experiment you did, the intervention you did. That's why they call the outcome variable as dependent variable in the experimental design. Why the exposure variable? That exposure variable is the training you did. Because training, yes, no. You train some, you didn't train some. There are two groups, A and B. You give training to group A, no training to group B. Education to group A, no education to group B. So when I say which one, if that group you belong to is a variable. Which group, A or B? Can you see now? So that is why that group, which is the exposure, is the independent variable. While the outcome, the education you are measuring, level of knowledge you are measuring, is the dependent variable. But it's just the same thing that you're describing in this way. So today, people just use them interchangeably. Whether you are doing experimental research or whether you are doing observational research, the variable that lead to something is the exposure or independent variable. The one that something is being is dependent variable or outcome variable. And one thing I want you to note here is that it depends whether something available is, it depends on which association you're looking at. For example, now, when you say association between level of education and employment status, we know that education is the dependent variable, is the independent variable rather, while the employment status is the dependent variable. But when you look at association between the same education and sex, you know that sex will lead to education. It's not the education that leads to the sex. The sex may lead to your level of education. Because your sex may influence whether you will be educated or not. So in that situation, the sex is the exposure, which is independent variable, while education is the outcome. Whereas in relationship between education and employment status, education was the exposure. Can you see? So which one is exposure or outcome depends on which two variables you are looking at together. You have to use, it's not computer that will tell you that. It's your common sense that will tell you that between these two variables, this is what comes first for this. So can you see now? So when we say comparing proportion between independent variables, it's looking at association between between two variables. And these two variables, what will be exposure, what will be outcome? So for example, now, if you are looking at you are comparing you are looking at association between level of education and employment status. In that situation now, or sex and employment status. In that situation now, sex is the is a variable, is the exposure now. While the employment status is the outcome, is a variable also. So the difference you are looking when you say you are comparing difference between groups is the difference between in the outcome between different group of exposure. In the outcome between different, so that shows that your exposure variable now, which is the independent variable exposure variable now, is categorical. There are group. Whereas in this situation for chi-square now, for this first one now, both the exposure and outcome, they are categorical. Compare proportion. Because when you say compare proportion, it means that if the proportion is categorical variable, you summarize with proportion, with percentage. It means it's categorical variable. Between independent group is categorical. So that's why another way of saying is that association between two categorical variables. So in that situation, is chi-square you use. Chi-square is for association between, that is, you have both exposure, you can categorize to, is it 2 or 3 or 4 categories? The other one you can categorize to 2 or 3 or 4 categories. Category. That's why you represent chi-square by constabulation. So one category will be along the row, another category will be around the row. You now do cross tabulation table to do it. Just know chi-square is for association between two categorical variables. And by nature, it's not parametric. Because you yourself, you know that is the variable is no number. So it cannot even be, say you are doing parametric, because it's only something that is continuous variable that follow, it can follow normal distribution. I see now. So you can also compare an observed frequency with a theoretical one. Measure of goodness of it. The meaning of measure of goodness of it, you have a theoretical frequency. For example, the one that commonly come to mind is ABO block group, where you can have block group A, block group B, block group AB, block group O, 4. So sometimes in a particular population, they might have done study before where it has established the relative frequency of each of them. Maybe block group A is 30%, block group B is 15%, AB is something like maybe 50%. By the time you look at both, all the three make 50. O is 50. Let's give you an example. So you may not want to, maybe in your own laboratory, you now see your own percentage, you calculate it. It may be slightly different, or maybe different from what they say is the one they have done before. You now want to say, is it the same? That your own percentage. Is it the same? You know, something may be different, observe the way you observe it. It may not be different statistically in the sense that that difference may be due to chance. You want to see if the difference is not due to chance. You want to see, are they the same or they are not the same? In that situation, now you compare your own frequency with that observed the theoretical frequency as measure of goodness of it. It's still chi-square you use. There are situations where you cannot use chi-square because not all the conditions for using chi-square are met. You now use Fisher exactness for that. So let's just move for when we get to chi-square, we discuss much about it because chi-square is not easy as people think. Though it's a common one you hear of, but there are many statistics that follow chi-square distribution. Now, the second one, compare proportion between peer observation. This one is still proportion. The peer observation means before and after. I think I've explained it before. Before and after. When you, for example, now, if you measure people's blood sugar pressure, you categorize them into hypertensive and you give me certain treatment for them. Later, after treatment, you measure their, for some months, you now measure their blood pressure to categorize them again. There will be some people that had high blood pressure before, they still continue having. Some people have before, they don't have again. Some people don't have before, they don't have now. Some people don't have before, they have now. You see that. But the issue is not even because of that. The issue now is that since it's the same person, it's not two group of people. that you did the assessment for and classify them into hypertensive and non-hypertensive. It's the same people you give treatment and now come to and do the blood pressure again. You will classify them also, whether they are hypertensive or not. So since it's the same group of people, that is what we call peer group. Actually, peer is a misnomer. Because when you say peer, people will be thinking that, oh, two group, you pair them. No. You say in each group, you take one, you pair them. No. What you pair now is the observation, is your measurement you pair on the same group of people. So what you pair now, somebody that you administer questionnaire, you say hypertensive, no hypertensive. Later, the same people, you now say hypertensive, no hypertensive. You have record for each person now, you have your observation. It may be years before, no. So for each person now, which classification before, which classification after. Is that classification your measurement that you pair on each person? Can you see now? It's your observation you pair on your subject. That's where it gets its name. But when we talk about independent group, independent means there are two groups, two separate groups. Just like this one, you say that you are comparing proportion between independent groups. Yes, we will know what is the proportion of hypertension in this group, what is the proportion of hypertension in the other group. There are two separate groups. That's independent group. So you have two separate groups, and you take their measurement. Two separate groups. So as you take the measurement, you have two groups of measurement, one for group A, one for group B. But for the peer group, you have two group of measurement, one before, one after, for the same people. Can you see that? So when you are dealing with categorical variable between before and after, you use what we call Mach-Nehmer chi-square. Chi-square is called Mach-Nehmer chi-square. Now, when you want to compare means of two independent groups, mean, that is, two groups, maybe mean now it has to do with quantitative variable. Maybe you want to compare the mean weight between two groups, class A and class B, their mean weight. You use the student t-test as a parameter. If the weight you can establish that follow normal distribution, you use student t-test. But if it does not follow, you can use non-parametric counterpart, which is Wilkinson, ransom test, Mann-Whitney test, or Kendall's test. Now, when you want to test mean of different impaired, can you say this is the mean? But for example, now you take people's blood pressure sitting, you calculate you record it, you can calculate the mean. When all of them will stand again, you take blood pressure for each of them. So each person has two measurements. So it's still paired. But this one is not categorical variable, it's quantitative variable. You want to compare mean of pair test, pair t-test to pair of two observation. You want to compare, you use pair t-test. If it's follow normal, if it does not follow, you use Wilkinson rank test. Can you see? Wilkinson ransom test is different from Wilkinson rank test. When we get there, you'll be able to see, understand better. Then comparing means of more than two independent variables. Can you see that? You will see that when we talk about the mean, first of all, say comparing mean of two independent variables. Then of pair variable. We now say mean of more than two. If they have more than two categories, it's a different thing also. Unlike chi-square, whether you are having a 3 group, 4 group, it doesn't matter. Chi-square is chi-square. But for comparing mean, that's where you are comparing proportional. Comparing proportion, whether there are 3 group, 4 group, it's chi-square for it. But when you are comparing mean, the 2 group of mean is t-test. But when you're having more than 2, 3 group, 4 group, and also it's ANOVA. So it's when we get to ANOVA, you're going to know the reason where you don't use t-test to compare mean that's more than 1 group. No, once in more than 2 group, rather 3, 4, you cannot use. Why you don't use t-test? We'll talk about it. If you want to determine, if you look at all these issues of chi-square and t-test, we just talk about it. You are having You can say the first one, chi-square, has to do with association between two categorical variables. The comparing mean, which is t-test, has to do with association between one categorical variable, which is what group they're into, group, either group 1 or group 2, and one quantity numerical variable, which is the the mean you are comparing. For example, comparing the mean blood sugar between male and female, as we said. So the factor male and female as sex is categorical, but the outcome variable, which is the blood sugar, is quantitative variable. So it's like association between categorical variable and numerical variable. That is, in that situation, you use even the same thing with ANOVA, because when you have it, that group factor is categorical, while the mean you are comparing is quantitative. But there's one when you determine the degree of association between two quantitative variables. The two variables are quantitative, therefore age and height for children. Age and height, how do they vary? In this situation, there is nothing. This is what we call correlation. In correlation, we call it Pearson correlation. In this correlation, there's nothing like exposure. No, no independent, no dependent. It's just that there are two variables, both of them are number. You see how do they relate, degree of association. That is Pearson correlation. All these ones are they have non-parametric counterpart. That is, if it doesn't follow normal distribution, you can use non-parametric counterpart. So now, lastly, determine the relationship between a quantitative dependent variable and other variable. That is, the dependent variable, which is the outcome variable, is quantitative. For example, now, we want to see a relationship between weight and, let's say, weight and age. So weight is the dependent variable. Relationship between weight and sex. Weight is still the variable. Can you see now? The exposure variable may be numerical, it may be categorical. When you say weight, age and weight, the exposure variable, which is age, is numerical. If you say sex and weight, the exposure variable, which is sex, is categorical. It doesn't really matter. In as much that the outcome variable is numerical, you use linear regression. The outcome variable, the exposure variable can be anything. Now, if you are determining the relationship between a categorical variable and other variable, in this situation now, the outcome variable is categorical. The exposure variable can be numerical, it can be categorical, it doesn't matter. The outcome variable is categorical. That is logistic. Does it make sense? So now, this is, I just give you a clue about the common hypothesis test you're going to do. Now, what I was discussing before, assumption around the hypothesis. What are the assumptions of using parametric tests? Now, even though we say normal distribution, but it's not only normal distribution, but that's the main one. There are 4 conditions, and these 4 conditions are arranged according to importance. The most important, number one, is normally distributed. For you to say, okay, you are using parametric tests to test something, that data must follow normal distribution. That's the most important condition, but not the only. Homogeneity of variance. Homogeneity of variance means the variance is the same. So, for example, now you are having 2 groups now. You want to compare their mean. Yeah, of course, now it's because the mean are different. That's why you want to compare it. Is there any significant difference? But their variability, that is, their variance, standard deviation, standard error, should not be different. Should not differ. Because if it differ, they are not comparable. So that's what we mean homogeneity. Homogeneity means across the group, the variability or variance is the same. It doesn't vary. That's homogeneity. The opposite of homogeneity is heterogeneity. Heterogeneity means that the variance vary across different groups. Homogeneity of variance. The third condition, data should be measured at least at interval scale. interval level. Here he's talking about, when you see interval level, he's talking of a what do I call it? Scale of measurement. Now you remember we have nominal, ordinal, interval, and ratio. When you say interval level, you know that it's talking about, it must be quantitative, because it's a numerical variable or quantitative that actually measure at least interval level. That's number that are carry number. So independent means that the measurement you are comparing, the two reading are not from the same people. But this one is violated in PIT test. And the reason it's violated is that I've already told you the conditions are arranged according to the importance. The most important is number 1, followed by number 2, followed by number 3. So number 4 is the least important. So sometimes you may not even need to meet number 4 before you go ahead to do your what do I call it, parametric test. Now, this one, how to check for normality, that one you just leave it. Is when we are doing demonstrating, what do I call it, carry expresses. That's where we do that. Now, in a situation when you have demonstrated that this thing is not normal, you have checked for normality. You check for normality by carrying out Gromov-Phillips test or Shapiro-Wilk test. It's a test you can carry out with expresses. So if you establish the fact that, oh, this data set is not normally distributed, what do? You do one of these, and this also is arranged according to, I didn't put number, but the first one is the most important thing you should do, the best option. When the second one is the second best option, the last one is the least option you should do. One, rely on the robustness of tests, and now go and carry out parametric tests. You say this thing does not meet criteria for carrying out parametric tests. But then I say, if you see like that, you can still rely on the robustness of it. A robust test is a test that is still valid when not all the conditions for using parametric tests are met. So when all the conditions are met, but it's still valid. So if you remember, we already said that even those conditions for using parametric tests, they are arranged in order of importance. If the ones that are not there are the ones that are not so important, so you can just rely on the robustness of the test and carry out your parametric test. The second option is to use a non-parametric counterpart. Instead of using student data, use my Whitney use or with thinking because it's ransom test. So if you will use that, then the last option is to transform the data. Because transformation, when you transform data, is not the same. For example, now, if you transform something into logarithm, you do logarithm transformation. The mean of that logarithm transformation is geometric mean. If you calculate the geometric mean, and now calculate the antilog, you expect it to give you the arithmetic mean. No, it will not give you arithmetic, it will be equal to the median. And you see, so that is the last thing you should do to transform data, because summa is now, how do we do this? Is it different type of transformation? Yes, I'll talk about that. Different choices of transformation. When you say you want to transform data, there are different choices. It depends on what caused the skewness of the data. So if it is positive skewness now, there are different levels. You can do logarithm transformation, reciprocal, or root. I will demonstrate how transformation affects data. In the next slide is there. If it is negatively skewed, you use square or cubic. You transform to square or cubic. If it is unequal variance, that is, if it is heterogeneity of variance, you still use the first one. The other one is, if you look at logarithm transformation, reciprocal, square root. The meaning of reciprocal is 1 over something. If you put 1 over, you change data set to reciprocal. The highest value becomes the smallest. You know, if you say 1 over 9 is smaller than 1 over 4. So, whereas in the original value, 9 is higher than 4, but when you put 1 over each of them, 9 becomes smaller than this. 1 over 9 becomes smaller than 1 over 4. So, when you do a reciprocal transformation, the original smaller value becomes bigger. The bigger value becomes smaller. Now, look at the logic behind transformation. Let's consider this value, x. X is the original value. And I list x 1 to 10. Just 1, 1, 1 interval. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You see the difference between one, each of them is 1, 1. But when you do power transformation, you square. If you square 1, give you 1. Square 2, give you 4. Square 3, give you 9. Square 4, give you 16, and so forth. You will see that as you are going like that, it's increasing in value. The x begin to increase geometrically. The distance begin to widen. Between 1 and 2, originally is 1 value. But look at their square transformation. So the difference is 3. Between 2 and 3 is 1 naturally. But between their square, which is 4 and 9, it's 5. Can you see? That's the way the distance between them begin to increase. So what square does, or cube, instead of cube, you can even multiply 3 times. 4 times 4 times 4, 2 times 2 times 2, 9 times 9 times 9. Can you see? The distance is even much. If you find the square root, it will reduce the distance. Look at the distance between 1 and 2, originally it's just 1. But look at their root. Root 1 is 1. Root 2 is 1.4. The difference between them is not equal to 1. So what root does, with square root, is to shrink the data, bring it closer. Why the square and cubic do is to make them far apart. So the logic behind, if you look at it, the source of transformation, the square and the cubic, you use it for negative skewness. When you have some value that are small outlier that is simply smaller than the rest. So we want to jack them up. Now, when you do square transformation, you try to jack them up close to all those ones that are the original, all those ones that are not outlier. That's the logic. But if you look at to correct for positive skewness, that's skewness to the right. That is when you have some big outlier, you find log, you find reciprocal, you find square root. Square root, you already say, is shrink it. So what you are trying to do, those outliers that are big, when you do transformation, it will shrink them to bring them down. But there's something unique about logarithmic transformation. Look at logarithmic transformation. You see, look at this scale. You see toward you see x, which is the normal value. And toward the upper part, you see log x. That is for each value of x. If you calculate the logarithm, look at it. Log 0.1, log 1 is 0. Log 10 is 1. Log 100, 100. Log 1000. What I just want to see that, can you see? The distance between the log is 1, 1. But this other one, look at it. Between log 2 and 3, the distance is 1 in log. The on ordinary scale is 100 to 1000. The difference is 900. Between log 1 and 2, in the log is just 1. But look at your normal scale is 10 and 100. The difference between 10 and 100 is 90. Between log 0 and log 1 is just 1. But look at the ordinary number is 1 and 10. So the difference between them is 9. Between minus 1 log minus 1 and 0 is 1 also. But look at this one, is on the normal scale is 0.1 to 0.1 to 1. So the difference is 0.9. So you can see that what log does is for smaller value, it jack them up. For a similarly bigger value, it brings them down. For a smaller value, it will jack them up. For a similarly bigger value, it shrink them. It's just like somebody collecting money from everybody, rich people, everybody, and not distribute it equally among the citizens. That's what. So for extreme value, it bring it down. For smaller value, it jack them up. That's long transformation. And that is why they use it also for positive skewness. In that situation now, even it can even be useful for one, because there are some letters that some are negative skew, some have some small extreme value, some small extreme smaller value, bigger value. But the one that prevail, it is the one that is more, whether positive or negative skewness, that will prevail. Now, I think that's the end of the lecture, just to give you a clue about assumption around hypothesis test. Issue of transformation coming. I just explain it also. Any question? Or you chat. You can chat or you ask your question. You can unmute and ask your question.
Okay, good evening, sir.
Good evening.
Thank you for the this. Thank you for the lecture. So, my question, I don't know. What I'm saying is that without looking, you were saying something about normal distribution, how we know if something is normal distribution or not normal distribution. But how do we, how, by just when we get the data to decide whether we are using the parametric test or non-parametric, how do we look at the data and now decide, okay, this is going to be, without analyzing it? I mean, the tests you talked about are what we are going to use to analyze it, but how do we now decide if it's going to be normally distributed or not normally distributed, even before analyzing it? I don't know if what I'm asking is making
So look
sense.
at the slide I show now. Look at, I skipped this slide. I just felt that when we get to where, if we are going to, because it's easy if I'm maybe one of these lectures introduce you to SPSS. So how you can hand-on, how you can run some analysis and do what you can handle data to use SPSS to manipulate data. So if you want to check for normality, this is what you do. It is just one of the. If you remember when we talk about the descriptive statistics, how you display data, quantitative display distribution. We talk about for quantitative, use histogram, all those bus and whisker, and
Pie
what I
chart.
call it, stem and leaf. All those ones, from there you can know if it's normally distributed or not pictorially. Then you
Okay.
can quantify the test. Look at this one now. I've shown you on this slide now. There are two methods. One is pictorial, while the other one is quantitative. So that first one, check normality visually. That is visually. This can be done by plotting a histogram, probability plot, or quanta plot. This one is quanta plot. So the meaning, we can run it with SPSS. The meaning of quanta plot, you remember we talk about quanta. Quanta is the when you divide distribution into 4 equal parts. So there are 3 points that divide them into 4 equal parts. I don't know if I make the illustration. If you want to cut bread for a set of twin, where you cut once in the middle, use half to the two. If there are 4 people you want to give me with that triplet, you want to equally, you are cutting in 3 places. You first of all cut in the middle, then for each of the half, you cut them in the middle again. So you have cut them in 3 places, they give you 4. Each of them is a quarter. Those 3 places that give you 4 quarter is called quartile. Are you seeing that? Quartile. And the positioning, the one that first of all you cut in the middle, that divided into half, is the 50% of the frequency. So the one that divides the lower half into 2, 25 is 25%, which is lower quartile. So the 50% is the middle quartile, while the one that divides the last one, the upper half, into 2 is their 75% upper quartile. That's why sometimes when they want to measure range, they say interquartile range. That's the range between the distance between lower quartile and upper quartile. So if you divide the data set into 4 like that, the positionally, and in the SPSS, there is a perfectly distributed data there. They divide that one to quartile also. That one is the one plotted along the vertical in this graph, which is the expected value. Expected number, that is, if you expect, if that is normally distributed, that's with the expected. That one, the data in that SPSS is completely, perfectly normally distributed. So in now comparing the quartile with your own data, which is the observed value, you know, if in a tug of war, if the strength in both sides is the same, it will be on the middle now. Nobody will push anybody. The middle line will still be maintained. Is what is happening. If let's say your own is perfectly normally distributed, you know, this point, the each dot is where your own value and the own data set and the one in the SPSS meet. So if your own is perfectly distributed like the one in the SPSS, like the expected, where they meet will be along the diagonal lines perfectly. For the fact that some it shows that it is skewed. Though you want to show that there are some outlier, smaller outlier, there are some larger outlier. The larger outlier at the top is higher. That will eventually is skewed to the right. It's positive. You can see that it's skewed just pictorially. But that, if you look, you plot the normal distribution also, histogram, or you plot the bus and whisker, you plot the stem and leaf, all those frequency polygon, it will show you pictorial. This is theta, it's not symmetrical. Normally, normal distribution is supposed to be symmetrical, you know, but still, you cannot quantify it. But you can quantify it by using 2 tests, Kolmogorov-Svinov or Shapiro-Wilk. That's what the research you see here. So look at 2 tests that tell the normality. So if you look at it, when you see SIG in mean p-value, it's a misnomer for the people that do SPSS. It says significant. Actually, it's supposed to be p-value. It's not significant. It is the value that will show you if it's significant or not. So that SIG, that's the p-value in SPSS. So when you write SIG dot, it means the p-value. So you will see that for both of them, for the both tests, the p-value is small. So when you are seeing 0.00, it means that it should be less than 0.01. It means that what it means that your own that distribution you are trying to test for the monomality is significantly different from a normal distribution, because it's comparing with a normal distribution that is already stored in the SPSS. I don't know if you understand. It's comparing your own with a data that is normally distributed, that they are programmed into SPSS. It now tell you that there's a difference. It means that if there's a difference, it means that your own is normally distributed. If there's no difference, it means that your own is normally distributed. That is why, because the one in SPSS you compare with is perfectly normally distributed. So for the fact that the p-value is so small, it means that your data is significantly skewed. Does it make sense? That's how to quantify it. Any other question? Any other one? If there's no other question, good night, everyone. So by yes, I think by next